Well, good evening to this second evening meeting entitled Designing for Seismic Safety and Resilience, Pipeline to Prosperity in Dhaka. And I just want to start by apologizing for the slightly late start to this evening meeting. We simply have a throng of people here in the audience. The room is full, so you can feel there's a palpable excitement in the room. This is, after all, our first in-person event since the November 2021 evening meeting. So it's a bit of an excitement that we are now back in the ICE and we are presenting to a live audience in the room, but also online. Before we kick off, I'd like to do a bit of housekeeping. First of all, for those of us who are in the room, if there is a fire alarm, it will be for real, and we will need to evacuate the room following the green signs. And we'll assemble outside on the corner of Storys Gate and Great George Street. If you have a mobile phone, please turn it now to silent. And if you haven't already done so, please sign the sign-in sheet. After the event, the bar is not open. However, there is a pub in Storys Gate called the Westminster Arms that is open, and other pubs are, of course, available. And tonight's evening meeting is also broadcast online through Wordcast, and hopefully it's self-evident how Wordcast works. If you have any questions during the event, please type them in the chat box, and please remember to give your name and affiliation as you do so. I want to say a few words about SECET's future events. On the 27th of April, we have another evening meeting called Developments in Post-Disaster Damage Assessments, SARAID Case Study of Haiti 2021. And that hasn't yet appeared on our website, but it should be up amongst the other events very soon. In May, we don't have any events, but on the 1st of June, we are co-sponsors, if you like, of a half-day workshop entitled Design of Steel and Composite Buildings Against Progressive Collapse. And that event will take place in the iStructures buildings here in London. It's a half-day workshop. It's free to attend. However, you do need to register before you turn up. And then on the 8th of June, we have the biggest event in SECET's calendar. This is the 17th Mallet Mill lecture, which this year is delivered by Julian Bommer. And the title of this Mallet Mill lecture is Earthquake Hazard and Risk Analysis for Natural and Induced Seismicity Toward Objective Assessments in the Face of Uncertainty. Tonight, however, we have two speakers who are both employees of Mott Macdonald. First of all, I'd like to introduce Barnali. She is a technical director at Mott Macdonald. She's a fellow of the Institute of Civil Engineers. She's a member of the SECET committee, and she specializes in earthquake geotechnical engineering. She was selected in 2020 among the top 50 women in engineering in the UK. And in 2017, she was the international winner of the Shamsher Prakash, I apologize if I got that wrong, Award for Excellence in Geotechnical Earthquake Engineering Practice. And during her long career, she has acted as a seismic designer and reviewer for high-profile projects around the world, not least in developing countries. And this is something we'll come back to later in tonight's program. The second speaker tonight is Jim Gelder. He is also a technical director at Mott Macdonald, and he's the global discipline lead for geohazards. He is an engineering geologist with over 25 years of experience, working on projects in over 60 countries in all sectors, ranging from thermal and hydropower through pipelines for oil, gas, and water to road, rail, aviation, and flood protection infrastructure. He He's a very keen advocate of embedding the UN Sustainability Development Goals into project delivery. And he's also advocating on mental health in the construction sector. He is a guest on the latest Breaking Ground podcast, the podcast of the Ground Forum. In tonight's event, Jim and Barnali will speak about the so-called Dhaka environmentally sustainable water supply project, focusing on seismic design challenges. And this project, as the title indicates, was placed in Dhaka, the capital of Bangladesh, where more than 18 million people face unique challenges, including a stable supply of clean water. But I will hand you over to the speakers because they know much more about this than I do. So without further ado, I'd like to hand you over to Jim to start with.
Andreas, thanks very much for that very thorough introduction. My name is Jim Gelder. I'll be doing the first sort of third to half of the talk, talking around the experience that Barnali and I have had for me for the last 9 years on this project. Before I do, I'd just like to pick up on the plug that Andreas very kindly gave me about the Breaking Ground podcast. It feels strange to be talking about a really uplifting talk on mental health in the construction sector, and even harder uplifting talk about suicide awareness. But I'd urge you to just Google Breaking Ground podcast and have a listen. There's a lady on there called Vicky Gutteridge from the Ollie Foundation who is absolutely wonderful. And it's the feedback that we've had so far has been that for such a difficult topic, it's a very helpful, constructive and uplifting talk. So I would really recommend, if you know anybody or if you're touched by that particular darkness yourself, I'd really recommend giving that a listen. Anyway, enough of that. I'm absolutely buzzing to be back, as Andrea said, in front of a packed lecture theatre here in Westminster. So I hope everybody that's watching online is as excited as the throng is here. I certainly have missed the adrenaline and buzz that comes from presenting in front of a live audience. And just looking, we do actually have one of those seats filled now, and a very, very intelligent face of Marcus, who the adrenaline of a too difficult question for him in the room cannot be circumnavigated by pretending that my broadband has just dropped. So it really is, all joking aside, it is great to be back. If you can, for future meetings, get yourself down here. I would suggest that you do. There's nothing like meeting in person, but we gather there's around about 70 people watching online, which is fantastic. And it's great to get that sort of coverage for the talk. So thank you very much, all of you who have joined online, to take the time to listen to me go on a little bit, and for Barnali to present all the wisdom of the work that we did. Tonight's talk then, there'll be a brief introduction to the project itself. Then I'll touch on some of the engineering challenges and talk about the ground conditions in Dhaka and what we were faced with before Barnali takes over and talks about really how we turn that into engineering outputs and a buildable design, and then finishing off obviously with some lessons learned, but particularly given the context of this project, some of the social impacts. So the project itself, the main lender is the Asian Development Bank, and the client is Dhaka. Bangladesh is one of the fastest growing cities in the world. It's also one of the most densely populated already. And so in addition to this pipeline, Dhaka have another 800 million, so just shy of £1 billion project for another water treatment plant and associated infrastructure at Bad 3. So there's a tremendous amount of in-ground engineering in the seismic part of the world. Sorry, I'll just go back. The engineers, this is engineers in terms of people doing engineering rather than the engineer. So Mott Macdonald are the client's engineer for what's called package 1, and I'll cover that in a moment. And we've also done the detailed design for packages 2 and 3. And package 1 is actually design and build, and that's a joint venture of Suez, OTV and Veolia, who are the Gandhapur Water Treatment SNC. So I'll talk about the project first, and here's some photos from when I visited site back in 2013, just to give a flavour for the sort of the vibe, the countryside, the people. My favourite of these 6 photos is the bottom centre one, where we consulted the village elder, who showed us the level of the highest flood in living memory, and that was used as a control on the hydrology and flood protection design for the project. We're not sure whether it corrected for the growth of the tree or not. A little bit of orientation. You'll see Dhaka just to the right of centre in Bangladesh. This slide is from another project I've just been working on, but I wanted to include it here just because it really brings home the immense volume of water that passes from the eastern and central Himalaya through the river catchments that run just to either side of Dhaka city. The river just to the right of Dhaka there is the Meghna River, which is the source of the water for the project. Zooming in a little bit, the slide on the left is Bangladesh, with Dhaka shown in red, and on the right you can see in purple that's the supply zone for the client Dhaka Wasa, and particularly to the right, the lighter zone is the vast area that Dhaka is expanding into eastwards. The population of Dhaka is forecast to grow to 29 million by 2035, which is up 11 million since I visited in 2013, and I can promise you it was busy enough when I visited in 2013. The Dhaka Wasa service area is 400 square kilometres, and they supply 90% of the population of Dhaka. And at the moment, the water supply is predominantly from groundwater wells in an aquifer that sits underneath the city, and I'll touch on the aquifer a little later on. But many of those are now failing either due to depletion of the aquifer or pollution of the aquifer. So we have a short video that just expands a little bit more on the background to the project and the social setting. So some really big stats in that video. This project to supply water for 4 million people, 9 million population growth, 40 kilometers of transmission water pipeline, large diameter pipeline, 1.8 meter diameters, and 50 kilometers of network water pipeline. It's a huge scheme. We're now looking at a slide that gives an overview of, in a bit more detail, of the project. So package 1 is the intake on the Magna River, with the intake at Barnali, and then 22 kilometers of untreated water pipeline, twin 1.8 dia pipes that go to the new treatment plant at Gelder. And that water treatment plant designed for 500 megalitres per day. That's package 1. That's the part that's designed and built by others. We are the owner's engineer, the lender's engineer, but we don't have time to cover package 1 in too much detail today, unfortunately. And package 2 is 14 kilometres of treated water pipeline from Gelder to the injection point into the existing network at Notum Bazaar. That's predominantly what we'll be talking about tonight. And then package 3 is the green and yellow, which is the new network pipeline within Dhaka city. This is just to help with the scale. This is a picture of the Magna River. It's a freshwater river flowing off the Himalaya that's wider than the widest part of the River Humber. Absolutely monstrous river. And that's the canoe, the motorized canoe that they took us on to do the site visit back in 2013. If anyone's wondering what I look like, I'm a lot more handsome now than I was in the picture there. Not going to dwell too much on this one. It's a satellite version of the schematic that I showed you. So package 1 in red, package 2 in green, and package 3 in yellow. What I do want to point out here, though, is the huge areas I showed earlier that Dhaka is expanding rapidly to the east. And you can see all those light areas in the center left of the screen. Huge amounts of hydraulic filling to get the land raised above the flood level for development and growth of Dhaka city. Just expanding on that a little more, if you look at the bottom 2 photographs, these are 5 years apart, and you can see the amount of reclamation filling that's gone on there. And then the 2 above, similar huge amounts of filling, but also you'll see how that filling and the evolving development plans over those 5 years actually made large alterations to the alignment of the pipeline. The magenta on the left was the original, and the red on the right is the final. Within package 2, there are 2 tunnel river crossings and shafts. These are standalone design and build packages, and we'll not be talking about those today, but there's lots of really interesting engineering, not necessarily seismic engineering, in those shafts and the tunnels. Package 3, won't be talking too much about package 3 this evening, and that's because Dhaka city is where Dhaka city is, because of something called the Madhopur clay and the Dupitilla sand, which is beneath it. The Dupitilla sand is this aquifer that I referred to that supplies the groundwater and has done since Dhaka was first established. But because of the clay on top, the liquefaction risk for almost all of package 3 was found to be low. So won't be talking much about package 3 either this evening, just package 2. So within package 2, what are we doing? Well, it's the twin pipelines that I've already referred to, but they're buried within a trench excavation, which, because of the space constraints, will almost exclusively be in a sheet pile cofferdam. as the ground engineers for the project, we had to get the information to support the temporary works design of the sheet piles and also the dewatering. Within the pipe, there's a trench backfill. So selection of suitable materials for pipe bedding and for general backfill. There's a real scarcity of any soil much coarser than fine sand within Dhaka, just because of where it sits in the delta flowing out from the Himalaya. So we had to specify the pipe bedding and backfill materials very carefully. Ductile iron pipes are subject to corrosion, so we had to assess the corrosivity of the ground and the chemical nature of the ground to allow the pipes to be designed for the in-ground corrosivity. And last but by no means least is the liquefaction mitigation that we're here to talk about this evening of the pipes, but also the pertinent infrastructure, air valves and washouts and the likes. So in terms of the ground model, when we started out, really almost nothing to go on. This area was almost completely undeveloped. What you're looking at on the screen there is package 2 and package 3 overlaid on the geologic map of Bangladesh, which helpfully shows us the Madhapur clay and essentially alluvial deposits, and tells us that they're all Pleistocene in age, but not an awful lot more than that. There's also a geomorphologic map, which is much more granular, much more detailed. And again, you can see the Madhapur clay in purple and the alluvials in green and brown that we were dealing with. But again, all we knew was that we would have sandy, silty soil to deal with. I really like this Google Earth view into Dhaka because it shows the extent of the Dhaka prograding from the Himalaya down into the Bay of Bengal. And what you can also see, we'll have to show you, is the Brahmaputra River that currently passes to the west of Dhaka, used to go to the east of Dhaka. And one morning everyone woke up and the Brahmaputra River wasn't where it used to be. It switched channels literally, well, almost overnight. But what we were able to do, and there's a picture of the typical material. It's a silty, fine sand, lots of muscovite and biotite mica in there. So it's quite a greasy feeling sand. It's not a great material at all. Across that old Brahmaputra alignment, though, we managed to find a cross section in a paper, and that pointed towards this pattern of an upper sand unit, a lower sand unit, and a mud unit in between the two. And that became really the basis of what the sort of thing that we were expecting to find within the project area. But obviously nowhere near enough to go on to start doing any sort of serious seismic analysis, so we had to do a ground investigation. And we had to do a ground investigation that met the state of the practice within Bangladesh. We tried getting interest from international contractors to see if we could do something a bit more advanced, but there wasn't really the appetite for international contractors to go and set up site investigation businesses in competition in Bangladesh. So we went with the local market and had some pretty state of the practice investigations by way of boreholes, SPT, permeability for that temporary works, design the dewatering assessment, obviously assessing the strata, getting some grading curves of the uniformly graded fine sand, index tests on the clay deposits that we got, and some shear box and triaxial tests to get some shear strength parameters. Always mindful with very high water table that it's difficult to get good grading samples from boreholes, so we did some trial pits as well. But the thrust of the investigation, particularly for the liquefaction assessment, was the CPT. And the CPT, we did Pisa cone to get cone resistance and sleeve friction,
We did some dissipation tests where we had clay deposits, but we also got them to use a seismic cone to get seismic velocity profiles through the deposits. Certainly, it was a first for our contractor doing CPT, and definitely a first doing seismic CPT. If it wasn't a first for the GI industry in Dhaka. And then I mentioned the corrosivity, so we did some winter resistivity test as well to get the conductivity of the ground. So in terms of layout on package 2, these are the borehole positions, notionally 1 kilometre apart, with clusters around the river crossings, and always, notionally 1 kilometre apart, but in places more closer together than that. There you can see the trial pits added to get the samples of material for grading tests, and then with the CPTs added in. So that just shows you the extent to which we relied upon the CPT. Really important for the seismic assessment, but also really important for us from a quality perspective, that we were able to get a ready assessment and acceptance of the quality of the CPT in a way that's much more difficult to do with boreholes. So some stats: we did 36 boreholes, 34 trial pits, 19 winner arrays, and 111 CPT tests. And if you were fairly generous and said 3 days for a borehole, that would be a 4-month fieldwork period. If you were extremely generous and said 1 day per CPT, that would be 4 months of field work. 34 trial pits, you'd definitely be able to do in a month. And 19 winner arrays, again, about a month's work. It actually took 6.5 months. And that was because the problems that we had with the CPT and the lack of experience and expertise. We were having to do a reasonable amount of upskilling of the contractor to make sure that things were done right. So here's a photo board of the site investigation. Most of the photos here of borehole rigs and sample storage, but those with a keen eye will recognise the photo in the top left from the video. And sat at the table is the wonderful Lucy Newman, who became something of a celebrity with the client. And with the lender, for giving the contractor hell pretty much every morning to make sure that the standards were first of all achieved and then maintained with the CPT. So Lucy and George Newman did a tremendous job during the site investigation. So just a quick refresher, this was the ground model that we had from what density we could do, an upper and a lower sandy layer with a mud layer in between. And here's what we found after our site investigation. So this is all of the holes and CPTs of the site investigation, with a water treatment plant, Gandapur on the right-hand side, and the injection points at Norton Bazaar at the left-hand side. And you can see that we found an upper loose sand layer, a middle clay and silt layer, and a lower dense sand layer. So it was really reassuring to see that at the grand scale, at the sort of whole pipeline scale, we've got the ground conditions that we were expecting, although obviously there's detail within that picture. Zooming in a little bit closer, these are the drawings that we produced. So you can see the upper and lower sand layers in green and the middle mud layer in sand. And zooming in on the detail then, for the boreholes, the blue lines are the SPT, and you will see all the SPT below 25 in that upper sand layer. The red, amber, green are the particle size distribution. So green is clay, orange is silt, and red is sand. And the circle, cross, and triangles are the Atterberg limits and moisture content. So we were able, at a glance, to get a really good feel for the conditions in the ground. And obviously you can see here that upper layer is really quite loose. On the CPT, orange and green for cone resistance and skin friction. but also we plotted on the calculated liquefaction settlement. But Barnali will explain how we got to that in a moment. But we had a version of this on the office wall where we had the whole 18 kilometres of pipeline on a single cross section with all the liquefaction settlements shown on it, so that we're able to draw lines on with a big marker pen. And I'm a great fan of doing things with marker pens on walls, as well as doing great things in the computer. So there you go. That's my introduction to the project and to the ground conditions. I'm going to hand over now to Barnali to talk about the stuff that you're all actually here for, the seismic engineering.
Thank you, Jim. Really great to be back at ICE and present in person. And Jim has already said that I was told that we have 100 people online, so at least people are listening to us. So the question then came, is Dhaka seismic? Do we have some seismic challenges? This project was particularly very close to my heart for two reasons. My mother originally was from Bangladesh, but after the displacement that happened when the country was formed, she left her family and went back to India. So when I got a chance to travel to Bangladesh, it was for personal reason as well, as I could see my mother's side of the family and look at the land from where she came from. So now coming back, starting to look at the seismicity of Bangladesh. Now, just important to note here that from tectonic point of view, Bangladesh is actually covered by three tectonic plates. You have the India plate, the Eurasian plate, and the Burma plate. Now, the India plate is potentially moving at about 6 centimeters towards the northeast, whereas on the other hand, you have the Eurasian plate subducting at about 25 millimeters per year. Similarly, the Tibetan plate is also subducting. So basically, the faults, if you look at the map that I have on the left, you'll see Dhaka is fortunate in a way that there is no major fault line which is passing through Dhaka. But it does have three major faults which are very, very important, to which I draw your attention to. One of them is called the Dhauki fault. The Dhauki fault is from east to west. It's about 300 kilometers fault. The other important fault is called as the Madhepur fault. So it's somehow the trade of, you heard the Madhepur clay name earlier. This is about 150 kilometers. And the last and the most other important, which kind of triggers most of the seismicity in the region, is the Sylhet-Assam fault. But Dhaka is not considered to be very highly seismic. It has not had any major big earthquake in the past. Dhaka is more known at the moment because of the flooding risk. So in fact, for climate change, Dhaka is one of the top cities in the world which is at the risk of climate change. So what I started looking at this project, I started looking at what are the earthquakes that have occurred in the vicinity of Dhaka. So this is 200 kilometers from Dhaka. We looked at some of the events, didn't find many events in the close vicinity of the city, but there were some big events, and obviously because of the proximity to the Himalayas, there were some further away events. But what was the problem was that some of these further events were felt in Dhaka city. But the record keeping was very poor. There was no proper catalog that you could do a detailed seismic hazard assessment study. And also the project, the information to do this kind of study was actually, and this is, we're talking about way back in 2014 and 15 when this project started. So we were really struggling with quality of information at that point of time. So we said, okay, let's look at what does the Seismic Code of Bangladesh says. The Seismic Code of Bangladesh was actually updated in 2012, BNBC. And according to that, the Dhaka, Bangladesh is divided into 4 category zones, which you can see: Zone 1, Zone 2, Zone 3, and Zone 4. And each of these zones is associated with a zoning factors. So Dhaka falls in Zone 2 with a zone factor of 0.2 G. Now, what this zone factor means, it's slightly different from what the way seismic hazard is in IBC or other parts. The zone factor is essentially associated with what they call as the maximum credible earthquake. And then the design basis earthquake based on these codes is about 2/3 of the maximum credible earthquake. So essentially the design criteria is that you design for the DBE, because it's an infrastructure project. So there's no dual level design, mostly designed for 475-year return period, if you consider it equivalent to Eurocode. That was what the code was telling us. The code was updated last 2012. We started looking at this from 2013-14 onwards. Recently also, there's been some probabilistic seismic hazard assessment studies. The most recent one is the Ziller study in 2019, where you can see in this map, there's 10% probability of exceedance in 50 years. So it's a 475-year return period. And most of the bulk of that is within that 0.1 to 0.2 G, or slightly between 0.1 to 0.15 G. These are bedrock accelerations. So kind of gives us confidence that, so at that time, the project requirement was to use the seismic code of Bangladesh, but we did a fair bit of desk study. Similar to that, following on from the seismic code, the next important thing is the site classification, which are known as site class A, B, C, and D. This is very similar to what we have in Eurocode, and the expectation is that this is classified based on the average shear wave velocity at the top 30 meters. And for most of the site classifications, we are at site class D, where we have a VS less than 180 meters per second. Okay, so initially, before we started the project, there were not really much discussion about liquefaction in Dhaka. The only reason why I became aware of liquefaction in Dhaka was I'd heard about what had happened in Jamuna Bridge, and there was some foundation reassessments because of liquefaction. So when this project was early on, I met the project director from Mott, Macdonald, and I just asked him, have you considered liquefaction? And at that point, he said, no, nobody has mentioned liquefaction to us. In this project documentation, there is no liquefaction. And that's how the whole process of liquefaction started. And then I started looking at the site investigation data. And obviously, what I was seeing was making me very concerned. Now, generally, for a typical liquefaction assessment project, many of my colleagues will know you can do it via SPTs, cone penetration tests. You can look at cyclic simple shear tests, cyclic triaxial tests, resonant column tests, and in many cases, which we do routinely, we go for very advanced models in softwares like FLAG, Plaxis, LS, Dyna, Swandyne. We can do a hell lot of things when you have the data for liquefaction assessment. This is all very good. But here we are in a country where really people have no concept of liquefaction. They've built all these structures. There's not much infrastructure work that's happened. So in such kind of environment, how do you begin the dialogue of liquefaction? That's the kind of challenge. And so one of the first things which we did, because we were fortunate that we could specify the site investigation. So in the site investigations, we said, okay, because we realized that we were in silty transitional soils, and liquefaction prediction in these soils is always very, very tricky. So we did not want to rely on the Japanese method, mostly on SPTs. We thought that CPTs would give us a better representation for the soil at this vicinity, and so we specified seismic CPTs. We thought that CPTs would at least give us a little bit better handle. We tried to schedule some cyclic triaxial tests, but obviously again here the country context comes into context. None of the local facilities that we visited had the facility for doing cyclic triaxial tests, so we would have to import samples here. So at the moment, we just went with the CPT tests. This is the typical CPT. I mean, as Jim already showed you, we had about 111 CPTs. So here is again where your digital and your data, because it's one thing to collect so much of data, and the second item is to discretize all of this data and to understand what the data is telling us. Fortunately for us, I'm just showing you one example of a typical CPT data where you can see the cone resistance is really. Now, remember, we are not trying to build some deep foundations here. We are just trying to have some pipelines, trench pipelines, which is maximum depth of the trench. You're interested in about 5 to 6 meters of the ground. And in that 5 to 6 meters of the ground, that's where we have that loose upper sand. which is the problematic sand for us. If you remember the ground model that Jim showed us. So at the top layers, we generally had very low QCs, less than 2 MPas. And the soil behavior index, if you use Robertson or any of this, was particularly in sort of silty sand, sandy silts. That was the kind of classification which we were getting. So not really such an easy material to characterize. We decided to use, we did liquefaction assessment through lots of spreadsheet-based methods, but in the end, because we had a lot of data, we decided to use the software Click. Whenever we use the software, we also made sure that we have done our own due diligence by calculating by hand and forming all of that. But in reality, what you are seeing here is a factor of safety. Liquefaction assessment is typically done by finding a factor of safety to see, and you typically want to have a factor of safety greater than 1.25. But all the bits which are in red here is actually telling you that the top 6 to 7 meters is liquefiable for this particular one, which we have picked up. The liquefaction assessments were typically done for a magnitude 7 earthquake. We also did sensitivity for magnitude 6.5. The peak ground acceleration is one of the inputs for our liquefaction assessments. This was taken as 0.18 G. Obviously, the numbers that you saw in the code was for MCE, and the design checks were done for the design basis earthquake. And you also had to take the soil factors. So the PGAs were about approximately 0.18 G. And most of because we also had the measurements, the shear wave velocity measurements, so we could classify the site, and most of the site was classified as site class T. The important point to note here was the CPT data. We followed the Idris and Boulanger's method because that was applicable for silty sands, doing the fines correction and following all the international best practice. I am not going into detail on that because we wouldn't simply be able to fit that within the time, but that's what we followed. We followed a lot of different methods. Whichever method we used, we came up with that there is a possibility of liquefaction. In this material, in this transitional material. It just does not have enough resistance for the applied shear loading that's generated due to an earthquake. Now, at this point, I was bad news for the project because I told 14 kilometers of the pipeline, and I just stood up and told them, guys, you have a problem, and there is a liquefaction problem for the pipeline. This was a cost which nobody had thought of, which was not in anybody's vicinity at that point of time. And so you can understand how the panics started throughout the project. And then obviously we all had to go back and scratch our brains to see what we could do. But one of the things that we started thinking, okay, there is a liquefaction problem in a pipeline. What happens if all of the pipeline settles uniformly? You are not really that worried. What are you worried in a pipeline? You're worried about the differential settlements. So we said, is there a way of predicting liquefaction-induced settlements? Now, those of us who deal with liquefaction on an everyday basis know it's impossibly difficult to predict liquefaction-induced settlements. So the numbers that the software gave us from a range of different methods, we took these numbers with a bit of caution. We didn't take these numbers as a gospel, and there was always a bit of engineering associated with it. But generally we saw, if you can see that liquefaction settlements, we're getting about 200 to 300 millimeters of settlement following this event. In the worst case, if the top 8 to 9 meters. Numbers range looks okay. And then obviously you saw the picture of the silt. I like this photo, and mainly because looking at this, it's quite difficult to say, is this going to liquefy or not? It's just not one of those obvious ones. This is very scary. This is what I used to scare everyone in the project. You can see we have all about 43 of these CPTs were in P2, and just shows the probability of liquefaction report. And you can see most of them, almost I think 75% of them was showing a probability of liquefaction more than 80%. Whereas only some people who were still doubting, they said, oh, the bottom ones, the green ones, which show the low probability of liquefaction, that was about 12%. So that was the number I was asked, how many don't show liquefaction? And so if you're looking at the image which is the overall probability for liquefaction. So that was bad news. then we said, okay, let's not panic. We had to calm the project team, the huge project team. And our strategy for trying to calm the project team was, let's look at the liquefied induced settlements. And we looked at the differential settlement across the route. So what you see here, the image on the left is actually a liquefaction induced settlement for all these CPTs. With the knowledge that these numbers are okay, following best practice, but they still are not the main truth or the only source of truth. And then on this, we marked the ones where you can see big reds are the areas where we knew that out of the 14 kilometers, we have to do some interventions here. We cannot have the pipeline and the trench there. And then we looked at all of the different possible cases. How could we do 14 kilometers of liquefaction remediation? It's too much. And so we had to come up with some optioneering, which is what I'm going to focus. What are the implications for pipelines in liquefiable soil? These are some of the images that we have seen in past earthquakes. I think the Christchurch earthquake had many images from the liquefaction, which we could see uplift, the soil around because of liquefaction. The pipeline loses all its support, and it can, in many cases, if it's not buoyancy, because of buoyancy, it might pop up. And there are many images. So there's some nice images from the Christchurch earthquake, which you can see, Garland et al. 2015, many documented case histories. So it is a real problem. You don't want your water pipelines, water mains to come up like this. So that was the time now to go back and look at ground improvement for liquefaction. There's huge range of methods for ground improvement for liquefaction. You can look at densification, where you have vibroflotation, vibro-rod methods, dynamic compaction, compaction by explosion, compaction grouting. Then the other part is reinforcements. Reinforcements are more common: stone columns, compaction piles, deep soil mixing. All of these are quite popular. And first choice, stone columns. Then you go to the more sophisticated ones, where there is permeation grouting, hydrofracture grouting, jet grouting, compaction squeezing, compaction grouting. And then the last solution is one of the most dramatic liquefaction solutions, which I recently saw in one of my other projects, was everybody said, the problem in liquefaction is because of the water table. Just lower the water table. So they were considering lowering the water table for the entire city because they wanted to reduce the risk of liquefaction, which I thought was extremely extreme. But then the other option is drainages. In many places, people are considering drainage, actually trench. So looking at all these four options, we said, okay, there are a wide range of methods, but what is suitable for our site? And that's where it comes down to what is suitable for the particular site where you are working, and the country and context. And I'll talk about this in a bit of detail. Also, we try to look at, are there any case histories where you have pipelines in liquefiable soil? What has been done before? What is in the published domain? Looking through vast trolls of literature, there may be more now. Remember, this was done in 2014 and 15, so it's quite, maybe there might be more cases now. But generally, people have kind of tried to form a bridge where you can have a soil cement wall, stop the liquefaction, where you have the pipe, do some sort of ground reinforcement below the pipeline, and normally use some compaction grout. And those are the kind of solutions which are available in public domain. What have they done in Bangladesh? Or did they have any experience? So this is what we found, that the sand compaction piles has a local experience in Bangladesh, because there was this project, a problematic project in Bangladesh, which is the Padma Multipurpose Bridge Project, which if you Google, you will see that project ran into a lot of problems. And one of the methods of ground improvement that was tried in that project was called a sand compaction piling. So why SCP? Because SCP, as Jim mentioned, they have got lots of sand. So they don't have to transfer the sand. It's locally available material. So it's kind of useful. And there was some very good case histories of this, which was seen in the Tohoku earthquake. In the picture that I have on the left, you see an improved area and unimproved area. Anybody who works in ground improvement, they always want to show this picture, because obviously the improved area was on SCP's sand compaction piles, and nothing happened to that after the Tohoku earthquake, whereas the other area where there was nothing was done. So it's a good one. So typically the sand compaction piles are used for clays, and it can be used for sands. It has been popular in Japan. It's very, very popular in Japan. In fact, there is a book which I'll just talk about, which is to deal with sand compaction piles. And for sands, it's mostly used for increasing the bearing capacity, for reducing the settlement, and for preventing liquefaction. These are the main bits where it's used. This, I think many people in the audience or people who have seen SCPs, they might know this particular slide. This is from the book that I was mentioning. Kitazume's 2005 is a book on sand compaction piles. And that is incredibly, he has accumulated all the case histories of SCP usage. And most of these usages are actually coming mostly from Taiwan, Japan, and the high seismic areas. In this, I will not go in detail, but it's just important to say that while this method, if you are coming to very, very stiff soil materials, then obviously people also use air. The air is used to break up the surrounding materials. And in this particular way, as you can see, in a selected way, sand is pumped into this, and the sand compaction piles are created. Typically, the design of sand compaction piles follows the same principle as stone columns, and you use what is called as the area ratio, how much of the soil you want to replace by your sand compaction piles, and you have the spacing of the piles. Any such type of testing needs to be, ground improvement is obviously, you need to test it in the site before a haver. So one of the things that we specified was that if we thought that sand compaction works in the site that we have, then we also specified that prior to using it on site, there should be a test trial to know the effectiveness. And this is usually done by measuring because it came from Japan, so they put a lot of emphasis on the SPTs. So this will come from measuring the SPTs before and after the SCPs. And normally the diameter of the sand compaction piles is about 0.6 meters. Like that's the kind of 0.5 to 0.6 meters. You're actually reinforcing the ground, allowing liquefaction pressures to dissipate, more excess pore water pressures to dissipate. So we could do, if we had a lot of money and the project was, unlimited funding, then what we would have said, yes, let's do sand compaction piles throughout the 14 kilometers, because everything is liquefiable. But then the question is that feasible? That would have made the project totally unviable. So our dream of providing safe water to so many people would go completely down the drain. So in that case, what do we do? This is the point where we got together in a team of not just the geologist and the earthquake engineer, but we involved our colleagues from the pipeline team and the structural engineers team. And we all decided that what is it that we can do which will give us security for the most vulnerable parts of the pipeline. And so this is the matrix that we came up with, which we call our risk-based matrix. So in this case, what we said, in some cases, we can accept the liquefaction settlement just using regular pipe joints, because these are steel ductile pipes. They can accept a little bit of movement and settlements. So in this matrix that you're seeing, what we have in the x-axis, we have liquefaction longitudinal differential settlements. So how much settlement the pipe can tolerate in the longitudinal direction. And in the y-axis, we have the infrastructure which is responding. What is the settlement tolerance of the structure? So obviously what we are trying to find out, if you have a control valve or a structure which cannot tolerate any settlements, then we will have to do a very high intervention there. So we focused all our attention on the red box, where we had structures which had a very low tolerate for settlements. So if the settlements, the structure will collapse. And also the liquefaction potential or the longitudinal liquefaction potential was higher. So in that red box where we said, in that particular limited portions, we will do sand compaction piles and other interventions. Whereas in the other parts, which were in green, where you have a lower liquefaction longitudinal settlements, as well as the structure can tolerate a high settlement, in those points, maybe we will just use pipe joints or seismic joints. So this kind of solution matrix could not have been done just by an earthquake engineer or by a geologist. We needed to involve all our pipeline people, pipeline colleagues who understood this much better than us. And this chart became quite famous because what we are trying to do in this chart, this chart was us trying to say where in the path, entire length of the pipeline, we are going to do some interventions. So we said, what is the maximum settlement that can be differential settlement that can be tolerated by restrained and unrestrained pipes? We put a limit of 250 millimeters. In reality, they can tolerate more, but we had to cap it at somewhere. And then this is the 250 millimeter is generally applicable if you have a long continuous pipes which are not connected to any hard spots such as chambers, shafts and others. But where we had chambers areas connected to hard spots, we limited it to 100 millimeter. So if you look at the graph here, what we have here are all the points. So the lines, there are a couple of lines here, and I'm just going to go through. I mean, this is where you need the audience in the room because then you can explain what these different lines are, but I'll try and... So the line in orange is first the differential settlements based on, remember we calculated the CPT based liquefaction settlements, and these are the differential settlements. There are many areas where you're seeing that if everything is settling uniformly, then you can see that the differential settlement is 0. Whereas in some areas, the differential settlement is about 350 millimeters, and some areas it's more. So that orange line is the differential settlements. Then we have another line, which is a line in gray. The gray is telling us that in areas where we have unrestrained or restrained pipes, we have a maximum differential settlement of 250 millimeters. And where we have crossings or hard spots, like canal crossings and other bits, there we limited the settlement to 100 millimeters. So that's why the line goes up and down, the gray line. And then finally, out of this, we had different type of solutions, some simple solutions. SCP is the most expensive solution on the table. And then there are geogrids and other solutions which we could use at different locations. So as this kind of gave us an idea that rather than looking at 14 kilometers of pipeline, we are looking at a much smaller area where we need to do the sand compaction piles. So this kind of chart was quite, by this time, our project looked more viable because we had said, okay, 14 kilometers is not the numbers. And we came up with all these numbers through discussion with the pipeline colleagues who told us what is the maximum settlement that these pipes can generate. So obviously we had to come up with some decision workflow. And the decision workflow was now it seems simple. At the time when we were delivering this project, obviously this was not simple because it went through, the main question was, is the pipe restrained? If the pipe is not restrained, then we had to come the question that are residual movements manageable within the angular deflection of the pipe joints? If it is yes, no further mitigation required. If not, we need to do the geogrid mitigation. So this is quite a detailed one. We don't want to go through everything, but essentially there is a logical manner in which we develop the solutions. So just going to talk about the first one, is the pipe restrained? If the pipe is not restrained, what happens then? So if we have unrestrained joints, except the liquefaction settlement just using regular pipe joints, because pipes on their own can deflect. And we said that for example, if we have a 100-meter pipe length, peak ground displacement at the center of 400 millimeters can be accommodated by the pipeline without loss of any containment. Because remember, we are having ductile iron pipes, DI pipes, which in their own way, they can deflect because of the shape and have a little bit of settlement which they can tolerate. So if it's within that limit, we allowed it. And for liquefaction design, we assume the target settlement figure is maximum. As I explained earlier, it's about 100 millimeters. So for these bits, we didn't have to do anything. Automatically, we made use of the properties of the pipes that we were doing with that. The second one is coming up to the question where we have to do pipeline mitigation. This is through movement joints. So here again, This is where, again, we started looking at each section of the pipe requires thrust block is restrained. And then there's a movement joint which is fitted at each end of the restrained section to manage differential settlements to a tolerable limit of 100 millimeters. And we know that the cast iron pipes are capable of taking significant amount of strain mobilized by joint articulation and axial displacements. And the extent of this would depend on the type of joint used. In the pipeline, we decided to have both unrestrained and restrained joints. So taking inherent ability of the pipelines and the restrained joints and the ability to movement joints, we kind of eliminated, and we made sure that this liquefaction induced movement is actually absorbed by the pipeline in the design. Now, what about the geogrid mitigation? Geogrid mitigation was our sort of a second order solution. Well, the standard geogrid reinforced matrix, which this is Jim's favorite solution, because what it does is provides tensile strength to the base of this. So we have twin pipelines, and then we have the geogrid at the bottom. Remember, we are trenching everything, and once we trenching this, we also have some geogrid wrap around, which provide the tensile strength to the sides and also the pull-out resistance for the base. So we wrap it around with the geogrids. And the geotextiles, obviously, they do the function of, they prevent the migration of the backfill into liquefiable soil. It provides a bit of confinement. If the soil below does liquefy, then obviously it is contained within this, because we are also specifying the backfilling material, which we make sure that it is non-liquefiable. And geogrids above the pipe provide extra flotation mitigation. So essentially, this is not a design requirement, but the pipe, so that it's essential to see that the pipe does not become buoyant in a liquefied environment. So this was a standard geogrid detail, and this is quite an easy solution because with the local expertise, ultimately, this pipeline is going to be built by local people, local expertise, local skills. Laying down lots of geotextile wrapping is easy, rather than trying to do something very, very sophisticated, which probably comes in a lot of problems. Then comes our standard sophisticated solution, the sand compaction piles, which we used for air valves and other places where we had the hard spots and around transition, because we can't go from just the geogrids into the sand compaction piles. We also needed a barrier of transition to manage the liquefaction in the surrounding areas. So in this case, again, the standard solution that you saw in the geogrid, all of that remains. But in addition to that, we have the sand compaction piles. So we designed the sand compaction piles. So they were mostly 600 millimeter in diameter. They had a spacing of about 1.5 meters, but each of at local places where we were doing the transition, we had the sand compaction piles at a larger distance. And the geogrid matrix from this becomes the pile cap to support the block of the pipe and engineered fill of the sand compaction piles. And so basically what I just mentioned, the geogrid standard detail continues on either side of this to provide the longitudinal transition. So we just didn't do it just at that area, left the sides, because from past experience of liquefaction, we have seen when you do ground improvement for one location and you leave the sides fail. And that ultimately creates an imbalance in the entire system. So we wanted to avoid that kind of sudden jump hard spots. And then this is the kind of drawings that we issued. In our drawings that we issued, because ultimately this is going to go to, this will be used, these drawings will be used to design, to look at what sort of mitigations we have. So for example, we are providing where we've classified the mitigations 1.1, 1.2, and what kind of mitigations we are giving, what is the dimension, how far do you extend on either side of the mitigations, and what is the liquefaction induced settlements. Everything is there in the drawings. So we spent a long time doing these drawings so that they could become useful. And so ultimately, in the end, we ended up having mitigations for those areas where we had hard spots, where there were some areas where obviously if we had to do a Madani Avenue, which we will explain in a bit later, where they were complicated to do. We decided, because remember, none of Dhaka has had any liquefaction mitigations. So if there is so we have to be careful of what the surrounding, we can't do a mitigation, but if the surrounding areas are not mitigated, then it's not very good for us as well. So, okay, so we've talked about a lot of things for you to absorb, but if you thought it's easier if you have some cartoons, because the cartoons will be actually showing up. So essentially, we're just going to show you one very nice video, and I don't have to do any talking.
This video short describes the design of measures to mitigate the effects of liquefaction of the soil for the pipelines of the Dhaka environmentally sustainable water supply project. The first area looks at Barnali Avenue, where the pipeline will be installed at the toe of an existing embankment that carries the road Barnali Avenue. The site boundary is very close to the road, and there is a zone of liquefaction that the seismic estimation has shown will be between about 3 to 5 metres thick. The road at the moment is on an embankment that's around about 5 metres high, and the soil beneath it will have undergone some static settlement, but no dynamics from the earthquake. As far as we know, no measures were installed to mitigate the effects of liquefaction for that embankment. The new twin pipeline will be installed at the toe of that embankment. To the left or south of the road, land filling is progressing in all areas and is gradually approaching the road, but hasn't reached it yet. Also ongoing is widening of the Macdonald road by placement of a new embankment, again with no liquefaction mitigation built in, although there will be some more static settlement, and this will impact. The main problem will be an earthquake during the period where the Barnali Avenue fill loads the liquefaction zone and results in shear surfaces and shown. These wouldn't take out the pipeline, although that will be mitigated in the long term by counterweight fill as the land filling reaches the embankment. As well as Barnali Avenue, there is also general trench construction, which includes phase 2 of the works. Here, the pipe is excavated below existing ground level with no fill to either side. Water table is typically very high, and because there's a narrow corridor for construction, the pipeline will be installed in a temporary excavation supported by sheet piles. Those sheet piles will be supplemented by dewatering wells in order to draw down the level of the groundwater below the required excavation depth. First of all, a mattress is installed at the base of the pipeline. This is to provide protection against liquefaction. Then there's a pipe bedding layer, some selective fill that goes around the pipe, and ultimately at the top, reused material, unselected, that's been excavated from the pipe. There are 2 layers of geogrid that provide the liquefaction mitigation by providing tensile strength around the block of engineered fill so that remains intact during an earthquake event. There's also a geotextile to prevent migration of fine material in or out of that block. When it comes to phase 2, the existing pipeline will already be in place when the sheet piles are installed and the water table drawn down. So this will result in some settlement on the pipeline. All of the static settlements and the dewatering settlements will be significantly less than that required for the liquefaction mitigation. So these are not considered to be a problem. But there is a slight challenge on phase 2 that there may not be the space for a temporary storm.
So I think you got a good fair bit of idea about what we were talking about, because you can do great design, but if you don't know how to construct and buildability, then we are always in a problem. So I'm just going to leave the state at which the project is now. The phase 1, the P1, is under construction. Our part will be constructed. So these are some photos. Now I've been looking at drawings. You look at 1.6 meter diameter pipes, but this is how big they look and how big the trench is. You don't see, unless you see it in sight, you don't get an idea. In paper, you drawing circles and they look like small pipes. But when actually you look at these photographs, this is how they look like. This is some site photographs, as you can see, trench preparation going on and men at work. So this is where the country and the context and the level of local skill and expertise is very important while we are sitting here and designing things. Again, you can see a height of the pipes. Looking at the person standing next to that gives you an idea of how big and wide this trench we're talking about. This is again some other construction photographs. From this, we talked about the project sustainable aspects. This is Bangladesh is very high on the UN sustainability projects, and it obviously for most of our engineering projects now we have to make sure that the UN sustainability projects out of the 17 obviously ensure availability and management of water and sanitation for all, which is SDG 6. That's applicable to this, whereas there are lots of other benefits as well, which you saw in the slide in the beginning. I'm not going to talk about them. Which kind of brings me to the key message. What did we want to talk about by talking about this project? We wanted to kind of try and bring to your attention, obviously everybody knows that liquefaction is a challenge for pipelines in Bangladesh because we've got high groundwater, moderate to high seismicity, fine sands and silty sand soils. The extent of liquefiable soil to the east of Dhaka is considerable. It has now come to my attention that many other projects in the area following on from this project, they've now started considering liquefaction, so which I consider is a big success for all the other projects in the region. Now, to fix the by ground improvement would make the project unviable. So we thought that the settlement intolerant infrastructures must be fully protected. There were many options, but we decided to go with SCP because it's a local norm, and for very large areas, deep soil mixing or piling may also be appropriate. And for other pipeline sections, it was tolerable to accommodate liquefaction settlements. So we did regular pipe joints in open ground, movement joints for restrained length beneath rivers or at thrust blocks. Investigation, we could do all of this because we had good site investigation data. So investigation is actually fundamental to demonstrating settlement that can be tolerated. We had seismic CPTs, and you saw all this we've not really touched on all the site investigation data that we collected. But of course, investigation quality was a challenge because I believe that before this project, there was no site CPTs done in Bangladesh. So this was the first project actually where CPTs were done. And liquefaction mitigation is a multidisciplinary, only one of the 5 workflows is seismic. It took us a big team, in-country expats, experts, and as I said, there's a huge number of people who have worked on this project. I want to acknowledge our team leader, Nigel Ostermans, and Chris Preston, who was our project director. And there's a lot of people still in site in Bangladesh, our colleagues in Bangladesh, because delivering such an interesting and exciting, challenging project is not possible without having a good team. Thank you for listening to us. If you're still around, we are happy to take questions. If we cannot answer some of your questions, we will go back to our pipeline colleagues who will help us, but hopefully. Thank you.
Yes, thank you very much, Barnali, and thank you, Jim, for a hugely interesting presentation. I will now invite those people who are listening online to submit their questions if you haven't already done so. I believe there should be a chat box somewhere in your interface that will allow you to submit questions. And once you've done that, I can then read them out to the presenters. But before we hopefully get any questions from our online audience, I want to turn to our in-person audience and ask if there are any questions. Okay. If so, maybe I can open the floor with a question. So, Jim, right at the beginning of the presentation, you discussed how there were 3 phases to the overall project.
Yes.
And you're responsible for phase 2.
Yeah.
Were there, to your knowledge, anything done on phase 1 to mitigate the liquefaction problem?
Yeah, for sure. So phase one is in very similar ground conditions. The difference between phase one and our work, so you saw in the video the Madani Avenue where there was the road on embankment, but with no mitigation measures for liquefaction in place. For phase one, to get to the intake site, they had to build a new road. The road has to be above the flood level, which meant that the new road had to be on an embankment. And because they were rebuilding that embankment, in the liquefaction event, the embankment becomes the problem. We were lucky that our pipes were just below ground, but for them, their pipes had this new embankment that became a loading factor in a seismic event. So yes, they had to deal with liquefaction. Their situation was in many ways more difficult than ours because of this embankment. They predominantly use geogrid in a similar sort of arrangement to us. But they also use geogrids within the embankment. So they had to put a lot of geogrid reinforcement into the embankment to stop the embankment from spreading and failing and taking the pipeline with it.
And it's also, I think, important that our work was also because the local universities in Dhaka, they were actually starting. There are some publications now where they're talking about liquefaction. And our work was also reviewed by the local university in Dhaka as well. So it's good. Now we can see the traction. When I started in 2014, of course, it was not there. But now we can see much more acceptance. And you will find many, if you Google liquefaction in Dhaka, you will see some papers now.
Thank you very much for the answer. I have just a bit of feedback from our online audience. Sylvie Britell, who is a project director with Antia, says, thank you for giving a glimpse into this huge project. Delivering a sustainable project is challenging. And she furthermore comments, I recognize that we are privileged in Europe, presumably in that we have more funds at our disposal to tackle these problems. And you also mentioned how it was a challenge to get the local workforce upskilled and working to the standards you were expecting.
So if I could just say bonsoir, Sylvie, and it was, thank you for that. Sylvie had the problem of finding the solutions for package one. She led the design effort there. So we know Sylvie well, and she's a great engineer.
So far, there's no further questions online. So if I may, I have another question, if I can ask you that. So you mentioned that the design earthquake was deemed to be a magnitude 7 earthquake with a peak ground acceleration between, was it 0.1 and 0.2 G or thereabouts. Was that a relatively close event, or was it a sort of a far field event?
I think it was the largest recorded is a 7.2, but that's not very near the city at all. It's a far field event. But I think the main, this is because of the alluvial soil there, the ground effects, and the fact that you can have the amplification of the ground waves. So we were using site class. Most of the shear wave velocities were giving us a site class D, where we had an amplification factor of about 1.5. So that was, I mean, we could sort of look at, as I said, at that point, there wasn't proper seismic hazard assessment. Now Jim has a model for Bangladesh, and United Nations also has done some risk assessment, earthquake risk assessment for Bangladesh. So now much more information is available, actually.
Thank you. We have a question from Vipul Kumar, who is a senior geotechnical engineer with Mott Macdonald. And his question is, hi, Jim and Barnali. Thank you for an interesting talk. In your opinion, what framework and incentives are required for experienced international ground investigation contractors to pick up work such as this one? I don't know if you got the question.
Yeah, no, I understand the question very well. I think that we thought that was the objective.
where when we started, we thought that the objective was, for thinking about our project, we want the best quality investigation that we can get for our project.
I think now it's a different question. The question is how can you upscale the local market? If you go back to the numbers I was saying at the start of the project, 11 million population growth, population of 30 or 35 million. You're not going to just magic an external supply chain into a country of that size. You have to work with what you've got and work to upskill. And that was why I stressed the fantastic work that Lucy did and how she became something of a celebrity for really sticking it to the contractor and demanding the quality that's required. And so I would say, Vipul, not to import the contractor and the experience within the contractor from overseas. You've got to work to upskill from within the local market.
Okay, thank you. We have another question from Martin Walker, who is a principal project manager also with Macdonald, and I think maybe you know Martin. His question is, while it didn't appear the strata were marginally liquefiable, was a site-specific site response analysis considered to check if the CSR would induce liquefaction across such a broad area and deep strata?
Thank you, Martin, for bringing that question. Of course, I think the answer to that question is, at that point of time, we did not do any site response analysis, mainly because we were kind of, as you know, with these projects, we did not have, first of all, we did not have all of the information to kind of characterize the site. We did start getting the shear wave velocities and other things, but part of my trip was in Dhaka was to look at these micro tremor shear wave velocity measurements, which were which were not actually adding up. So there were lots of difficulties at that time. So yes, we did not. But I also wanted to kind of show the Professor Yusuf Hashash's work in the NSF thing, where he's kind of said that these empirical methods of liquefaction assessments have been developed with some assumptions where you calculate the CSR in the way that they are calculated by using the empirical formulas. It's there in his national NSF lecture, is kind of saying that trying to do calculating the CSR by using these kind of advanced methods of doing site response may not be suitable for the empirical methods. So that was one of the reasons why we didn't do it. But of course, I agree with you. Perhaps that's something which maybe we could do when we go back. There's another project now which Mott is working on, which is a sister project, which is the largest water treatment plant. So all the experience that we've had in this one can be transferred in that project. Thank you for your question, Martin.
And I think we have time for just one final question, but it has to be a short answer.
You have the wrong panel for that.
It's again a question from Sylvie. Did you get a chance to install monitoring for both earthquake and displacement?
No.
Okay.
You wanted a quick answer, you got one.
You can elaborate if you want,
Yeah.
but
no, we haven't. I think that would need to be trans-body. So we're dealing with the Water Authority. I think if you could get at a high enough level in government to draw together the Dhaka Wasa, the roads, the aviation, the rail, who generally have a higher ranking, then you might get some kind of national scale monitoring system developed, but you wouldn't get it just on the back of one water supply project.
Thank you, Jim. Thank you for that answer. We do have two more questions. I'm afraid we have run out of. Oh, you sure? Okay. Right. Okay. Barnali insists we take the questions I do apologize. We're going to run slightly over time. I hope our audience doesn't mind. Of course, if you're online and you have other business, you can log off anytime you want. So the question comes from Ian Smith from Atkins. He's a technical director with Atkins. And his comment and question is very interesting. Thank you, Barnali and Jim. A real education in how to work in such challenging locations, such wonderfully committed local people, and some very fundamental engineering being carried out by you and your team. Amazing. My question is, wasn't the issue in the images of floating pipelines at other sites due to their mean bulk density being essentially close to that of water, and as such, they float when the density of the surrounding soil is probably closer to somewhere between that of, fortunately, the question is now truncated, but maybe you get the gist of Ian's question.
Yeah, indeed. So flotation can be an issue. We actually looked at the density of the whole block. We've got a block of compacted soil built within the trench sheet piles with a geogrid wrap around it, and the density of that block was certainly sufficient to resist flotation. Also, Barnali showed on one of the slides that we do have 2 layers of geogrid above the pipeline, and the latest research that we've found suggests that actually if you can put 2 or 3 layers of geogrid above your pipeline, then the risk of flotation is significantly reduced. Also, there's the density of the ductile iron pipe versus HDPE, which gets us a denser overall unit. So we did look at flotation and decided it wasn't a significant issue, but we had got some protection in places as well.
So here's a question from Ryan Farmer, who's a chartered civil engineer, and he even apologizes for being from Macdonald. So his question is, it seems like we were quite close to missing out on the liquefaction risk, as it was raised midway through the project. It also seems that the risk was not well known prior to 2013. Have any reviews been undertaken of projects in the past which may have risked the risk? And if so, have any remediation measures taken place?
The answer to that question is really from, if you look at the infrastructure projects that have actually been built in Dhaka around before that, there's not much information about liquefaction. It was mostly in the academic papers, but it was through some academic publications, more papers. And there was a problem is the bridge that we talked about, where there were some issues, but that was mostly with micaceous sand issue. That's when this discussion started. So when we came into the project, we kind of very early, when we had some tender documents, they had identified that, but it was not so extensive that what we found out to be later. But it was obviously sort of things with the more awareness. And now, as I said, I have seen myself now specifications from others for these projects where they are routinely talking about liquefaction. So liquefaction is now a common part in the terminology of the infrastructure developments in that region.
Yeah, I'd also say that when I came to the job in 2013, there was a feasibility study for the 18 plus 22 pipelines, and of that there were 10 boreholes. Yeah. And those 10 boreholes showed sand with SPTs around about 10 in the top layer. So we did know liquefaction was a potential issue, but there was a long road to travel from there to being able to get the level of detail that you could use to communicate and convince people that hold purse strings. So technically, I think we knew the issue was there right from the start, but there was a journey to walk with others in the wider project team to get them to comprehend the scale of the problem and what it meant. And then there was this journey that we've tried to describe tonight of
identifying the problem, coming up with the solutions that will fix it, then knowing that those solutions make the project unviable, and then having to take a step back to something more pragmatic.
And we want to say thank you to all our Mottmac colleagues, because actually we have not given this talk internally as well. This is the first time we are speaking about this project, because we've been waiting for the site work and everything to finish. So this is actually the first time we are speaking about this project, both internally as well as externally. That is why so many questions.
I see. Okay. Well, it's been hugely interesting, and I'm sure that if you decide to give this presentation to your colleagues at Macdonald, it will be a very interesting event. But for now, I'd like to bring this event to a close. I'd like to again thank Jim and Barnali for their time tonight to come and present their work they have done in Bangladesh. And I'd like to also thank our audience for showing up. Let's give each other a hand. And finally, and last but not least, I'd like to thank everyone who listened in the online broadcast. Thank you very much, and good evening.